Hello, and welcome to Module 2, Principles of Energy. And we're going to be discussing some of the basics of energy. And to start out with, we're going to talk about just categories. So just the categories of energy and its mechanisms. And so here is the book table on the different forms of energy, or the categories that I can stick energy in. And so we have chemical, nuclear, radiant, thermal, sound, electric, and mechanical, which is kinetic and potential. With that said, I can stick some of these, like chemical, into mechanical energy. For example, chemical, when it's inactive, is in potential, and then when it gets started in its reaction, I could call it kinetic, it's in motion. So mechanical is a bit of a shaky form that I can stick some of these other forms into. The reason for the categories, while it is all energy, is just to help break down and help us understand more about energy in general. So without further ado, starting out with the law of conservation of energy, that energy is constant in the universe. It's not created, it is not destroyed, it's just changing form. And so this is a picture just giving you a little bit about different form changes. The first one is chemical energy. And so chemical energy basically has two reactionary types. One is the endothermic reactionary type, and the other is the exothermic reactionary type. Endothermic being energy that is going to be absorbed into the system. And so that means the outside world, more or less, will see a little bit of a temperature change, where the outside world will get a little colder. And exothermic is a releasing energy, so it's going to give it off, and that means the outside world might get a little warmer, for example. So that's form changing. A great example of an endothermic chemical reaction in nature is actually photosynthesis. So you think of plants making sugars as foods, and that is a great example of endothermic reactions. Another one that's great is those poppy packs that you use when you are injured and you want to take care of a bruise, and you pop the pack. That's making an endothermic reaction. The chemicals are combining, which is stealing heat energy from the world around it, making the bag cold. Exothermic reactions are the ones where we give off energy, and the best examples are anything that makes an actual motion, so kinetic, or light. So we're burning something, we make a little bit of radiant energy, or heat, thermal energy. And so those are great examples of exothermic chemical reactions. But while the item is inactive, for example, that log of wood that I'm about to burn, it's just in storage. So it has chemical energy potential, but it's stored at the moment. The next category is nuclear energy. Now, this is very different from chemical energy because now we're talking about the nucleus of an atom. So going back to high school when you learned about atoms, or even middle school when you learned about atoms, and you have your atom, and inside you have your protons and your neutrons. Outside of your atom, you have your electrons. If I take the nucleus, the interior part of my atom that has my protons and my neutrons, and I change the number of protons or neutrons within my nucleus, specifically protons, protons within my nucleus, I can get a fission or a fusion reaction. Now, if I'm having a fission reaction, I'm removing protons from my system. If I'm doing a fusion reaction, I'm inserting extra protons into my system. When we think of fission and fusion, we often want to think of fission as being huge releases of energy, and fusion actually requires energy input, so we can think of it more about creating a battery or a storage of energy in the action of fusion. Next category is radiant. Radiant, or electromagnetic radiation, is wavelengths of light, or I can measure them as individual particles, photon particles, and this is what we think of as our light energy. Radiant is one of the most common forms of energy use. You think of your computer screen right now, I'm producing light, right? So it tends to be an end form. So when we talk about that law of conservation of energy, that I'm changing from one form to another, radiant energy is a great example of wanting to change everything towards being light. And so it tends to be an end use, or a final form that we're looking for in our energy chain. This is an example of absorption of light into a solar cell, which that solar cell is now being used as a battery because I'm absorbing it and I'm converting it into electrons, so electrical energy. And that electrical energy I can then use to do something mechanical, like turn a engine system, like a little turbine, as you see in the little picture. Thermal energy. Thermal energy is a transfer energy, tends to be intermittent. So, for example, a lot of what we do when we burn fossil fuels is we're trying to boil water to make steam, and that steam then turns a steam turbine. And so we're transferring or creating a transfer of energy through heat, thermal energy. So thermal is a very popular transferent energy. One of the few renewables that we think of with thermal is the act of using thermal geothermal. So the Earth's natural heat within it and using the reactions that are going on in the center core of our Earth as a heat energy source on the surface. And so geothermal is a fun one, and that won't come till the very last set of chapters and modules in this course, but I'm excited to talk to you more about thermal as well. Now, one of the energy forms that gets the least amount of love is sound energy, and this is a deformation energy. It's actually a mechanical energy. I am deforming or changing the shape of the fluid around me. So, for example, right now I'm talking to you, and there's atmosphere around me. And so I'm changing the composition or shaping of the atmosphere, allowing me to send sound waves at you currently, which you're interpreting in your ear as you're feeling those vibrations in your eardrum. So sound energy, we're deforming the fluid around us, and we can use sound energy as a form in any type of fluid. Some fluids work better than others. Atmosphere is a great one. Liquids can be okay when it's waters, but when we get into metallic liquids, sound does not travel well. It doesn't deform well. It's not enough motion. We need more bang for our buck to actually get that movement. But sound energy is often a waste energy. You think of yourself when you walk under a transformer box and you hear that buzz from excess energy that's being sent off, that's not being condensed back in. And so we can often pinpoint a problem with a system if there's a lot of sound energy that has its waste. It's one of the ways that we can create a sustainable practice if we see a lot of sound energy, is to create a buffer on that sound energy so we're losing less energy towards that action of sound. The final form of energy that I'm going to talk to you about is electrical energy. Now, electrical energy goes back to that atom and the exterior of the atom, where I have my little electrons in their valence shells spinning around. And in electrical energy, the way that we're forming it or pushing it along is by bouncing the electrons out of one valence shell into another valence shell. So we're actually making electrons jump from atom to atom. And so things with a metallic bond, something that shares its electron bonding in sort of a soupy form, is better at allowing electrons to jump through it, hence electricity working best in metals. So this is all interconnected. Electrical is one of the fun ones to harness. And one of the things to keep in mind is in most electrical energy, or in like a wire system, the electrons will technically bounce in any direction. It's the constant charge of energy coming in one direction that pushes it forward to the outwards direction. A superconductor is when all electrons actually move in one direction in its own state. So that's what we consider a superconductor. That's also why energy can be left over in a line, even when the line's disconnected, for a small amount of time till those electrons resettle themselves into their valence shells. And that's why you can still get zapped with a product even when it's disconnected if you touch it too quickly afterwards. The final one, and the category that I said many of the other forms that we just talked about can technically fit into, is mechanical energy. And mechanical is the energy of motion, things in action or movement, going back to that muscle activity. And so mechanical, once again, has two forms: potential and kinetic. Potential is the stored, kinetic is the active, and we can pretty much put those things into those categories. And here's some examples of an active system of a water wheel and a wind turbine. And so that's a good setup for forms of energy, and I'll meet you back for part 2 of Module 2.